Hi everyone, Reese here with Cranberry Alarm Ri3D, and I'm here with
Jordan.
And Corey.
And today we're going to be going over our day 3.5 or Tuesday overview of our robot and where we ended up after our 3-day challenge, and talk about all of our systems, how we integrated intake, hopper, kicker, and shooter into our robot to be able to score fuel into the hub, and along with some future considerations that we would make to basically play the game better than what we are doing currently now.
This video on fun is brought to you by our viewers, supporters, members, and also in partnership with the following. Build your alliance with so many other FRC alumni who go to Kettering University. Every student at Kettering experiences our cutting-edge co-op programs that seamlessly blend the professional and academic worlds. Kettering co-ops are a fully immersive working experience at the leading edge of industry. Head on over to kettering.edu/FRC to learn more about their incredible programs and to get more information. AndyMark is your one-stop shop for all things at FRC REBUILT. Be sure to stock up on your rebuilt game-specific elements right now at andymark.com. Plus, check out the newly released products to help your team, and don't forget to stock up on bumper materials and kits. Head on over to andymark.com to get the superior service and reliability that teams expect.
So to go and kick it off, we'll go ahead and kind of go through the progression that the ball would kind of go through the whole robot. So to start, we'll go ahead and talk about our extendable hopper and intake, as these two are kind of closely related in how they're going to kind of operate. To start, as a quick note, we are not currently actively extending out our hopper. This was purposely done because we knew in our time constraint we wanted this to be a focus that we did at the end. However, we kind of ran out of time and wasn't able to make this a big focus. But we know that there are many solutions that you can employ to make the hopper stay stowed within your starting configuration, and 2, actively deployed. So our main solution to this would basically be using the intake to hold the hopper in starting configuration, and then as the intake deploys out, the hopper would then release and deploy out via some springs or some surgical tubing. And this is just using some shoulder bolts here on some guide rails, heavily inspired off of 254's 2017 robot. For our intake, we're powering this intake pivot. This is a normal pivoting intake right here. We're powering it all off of a Max Planetary on a 25-to-1 gearbox, and then an 18-tooth pulley powering a 60-tooth pulley. And that's all driven off of one side here, and the other side is being pivoted via this peanut bar right here, extended across it to help maintain that the two sides are synced. We're driving the belt coaxially via this set of pulleys right here. And that goes down to an AndyMark Sport Gearbox 4-to-1. And from there, we can pivot this however we want, and it's very light since there's no motor attached to it, and we can continue to do whatever we want with it, and we'll still be able to drive the intake in whatever position it is in. We pivot the intake down, and from this position, we'll have, you've got a ball nearby. Thank you. Corey, do you want to go ahead and talk a little bit more about this?
Sure, yeah, I can talk a little bit more about the intake design we ended up with. We tested a few different types of wheels and roller bars. We tested AndyMark compliant stars, ThriftyBot 4-inch compliant wheels, and this AndyMark silicone tube roller kit. And the one that we ended up going with on this robot, as you can see, is a silicone roller kit with ThriftyBot dead axle on either side to drive it. But a little bit more about the design. You can see on the side profile that we have this backer bar here. We found that when intaking the fuel, it's really important to have something other than bumper material in contact with the fuel to get a consistent and reliable intake. But the compression that we're running here, the center of this axle is 5.5 inches off the ground and is around 5 inches to the backer bar. So around 1 inch of compression with the backer bar and a 1/2 inch compression with the ground. If you have too much compression with the ground, we found that the fuel kind of sit outside the intake and just roll. If you had a more compliant intake, then maybe the intake would bounce out of the way and pull the fuel in, but we're going with a rigid driven pivot, so that wasn't an option for us. But Yeah, I think that's a good overview of the intake. Do we want to run the intake? I'm going to go and have Reese bring the intake back in, or I can do it. So right now, as Reese mentioned, this roller bar is running on a 4-to-1 with a sport gearbox. We think that we would like a lower gear ratio for the roller bar to be spinning faster, but we didn't end up having time to change it or do anything different. As you can see, it does pretty well at touch it, own it, grab the fuel, pull it up into the hopper. We found that sometimes if your hopper is a little bit too compliant on the edge, your intake roller can take the fuel, push it outside of your hopper through this gap. With a little bit more time, maybe some more structure or rigidity to the hopper can fix that. But that's how our intake's looking so far. We're happy with it. We think that there's some changes to make that you guys could do to improve it, but the most important parts are compression with the ground and the backer bar, and having something back there like a backer bar or other material to get a consistent intake.
Yeah, and so our plan right now is that basically we'd be driving around the match with our hopper out the whole match. So once basically it deploys, it'll stay out the whole match. I think there is definitely some mechanical magic you could do to basically get everything to fit up. Basically with the intake, when it comes up, it actually pulls the hopper back with you. And you can see we're using these little fins right here, and this basically helps kind of keep the hopper stable and tied to the intake per se, without actually being attached to it. And this kind of really helps with the floppiness that we see from the intake and keeping everything rigid. So you can see here, the hopper becomes very, very floppy without anything there. So we'll maintain this position somewhere kind of elevated right about there whenever we're driving around in the match, and that's kind of a good position to hold all the fuel inside the hopper and allow us to drive around. Then when we begin indexing, our plan was to agitate like this, and then maybe finish with a big swing like that to basically get the remaining balls into the hopper. But while we got a bunch of balls in the hopper, let's go ahead and just do a live test of the hopper, and then we'll go ahead and talk about what's going on there. I'll go ahead and adjust the shooter. So we missed every ball because we were aiming wrong, because I don't know how to orient the shooter correctly. But as you guys can see there, we do a good job of funneling all those balls out. That was probably 30 some odd balls, and that we managed to cycle through in 6 seconds there. So we were cycling right around 5 balls per second through the hopper, which I think is a great benchmark. Ideally, we would have been able to do 10 fuel per second, but we're really happy with what we're seeing with the 5 fuel per second. So to get into the specifics of it, the main concept is we're using the polycarbonate sidewalls to retain all the fuel, and then we're using a hopper floor that's powered using the Andy Mark silicone tubing, powered by the Thrifty Bot idle tube rollers. As the fuel makes its way through the hopper, it comes to 2 sets of Thrifty Bot 2-inch vectored intake wheels, and from there it biases the fuel towards the center. And from here, the 2 compliant wheels here in the center force the fuel into the kicker assembly. And so this was something we played around a lot with. We had originally these 2-inch stealth wheels here all throughout the bottom. We had too much grip, and it would squeeze the game piece, and this ultimately just didn't work out well. We switched to the Thrifty Bot vectored intake wheels on both sides, and this was really the sauce that we needed to be able to get the balls moving the way we wanted to. We still occasionally have a jam here and there, but as you guys can see, moving those balls through was fairly successful for us. So let's go ahead and load it up one more time and do another quick test while I go ahead and talk about it. Go ahead.
Yeah, one thing to note about the fuel, we haven't talked about it yet in this video, but have mentioned it several times in our previous videos. The fuel don't compress much, so your mechanisms are going to have to be the compliant part. And Reese was mentioning how we had stealth wheels all along the bottom, but the fuel was kind of just getting jammed and getting stuck. It's because the fuel don't have as much compliance as previous game pieces, and so you have to interact with them a little bit differently as they move throughout your robot. We're going to do one more full hopper test here, and then I kind of want to get some close-ups of individual fuel in the hopper kind of moving through and talk a little bit more about some details we found. Spinning up the shooter now. You can see that occasionally we have a little bit of a dead period where fuel aren't moving through the hopper, but it works itself out. I'd like to point out these zip ties that we've added to a couple of the rollers. Without those agitator pieces or the zip ties, the fuel would sit and spin and just treadmill on two of the rollers, and so we would end our outfeed into the shooter with like 4 or 5 fuels still in the hopper. But all it took was a little bit of agitation, and that fixed itself. Let me get rid of this fuel. I guess we would have to fix that for a final robot. But I'd like to show individual fuel moving through the hopper because it's really impressive what these 2-inch vectored intake wheels are able to do with the fuel if you've got the compression and the setup right. So let's go ahead and see. And then Reese, I'd like you to, when the hopper is stopped, just set a fuel in the corner of the vectored intake wheels. This is really impressive. And after we did that test with vectored intake wheels on the bottom and top, we were happy with that and pretty confident that this would be able to avoid jams for the most part and feed the hopper feed the kicker at a good rate.
Yeah, so that about does it for the hopper. I guess to end off with a few improvements that we would want to do for this mechanism. The big thing would be dialing in the whole hopper sighting, making so that it's maybe a little bit more rigid in a few more places, making sure that it's actually actuatable and does everything that we want from it. So we can go ahead and move on from there, and we can go ahead and talk about our next step in the path, which is going to be our kicker. This is a fairly simple mechanism per se. But this is basically a set of wheels that its job is to move the ball from the hopper into the shooter. And so we're running a set of 2 1/4 Andy Mark compliant wheels on the bottom there to basically move the balls, to move the fuel through the kicker. And this is all being done with about 5 inches, or with about 1 inch to about 3/4 of an inch of compression. Our center to center distance was about that much, but then we ended up separating the Thrifty Bot wheels just a little bit to reduce compression to help the balls go through a little bit smoother, and we found out that worked out really well for us. And so that was all just a little bit of fine tuning to figure out what worked well, but ultimately we're happy with what we're seeing from the kicker and its ability to move the balls up through. And we're all powering this from 1 Neo off a 4-to-1. And yeah, and for improvements for this mechanism, really don't have a lot of improvements for this mechanism. We're really happy with what we're seeing from it. Ultimately, we want this to be going as fast as possible. We're powering, like I said, we're powering off a 4-to-1, and it's going from a 40 to a 32 tooth gear train with a finishing ratio of 3.2 to 1. And it's important that this gets a bunch of speed on the ball so that as the ball arrives to the shooter, it already has a bunch of velocity. Therefore, we can maintain consistent shooting from ball to ball. So ultimately, we're really happy with what we're seeing there, and we can go ahead and start talking about the shooter. Do you want to cover this?
Sure. So our first take at the shooter, our first prototype, was to take the Andy Mark launcher in a box. Thank you to Andy Mark for supplying that. Just set it up at a fixed angle and try out some shots. The Andy Mark shooter in the box is everything, or launcher in a box is everything from this plane up. So the side plates, the churros, and these 4-inch stealth wheels come with the launcher in a box. you'll notice that the side of the stealth wheels have the AndyMark flywheel add-on, and that just gives it a little bit more inertia. The process of fine-tuning this shooter and getting a good compression was pretty simple. They have these gridded side hole patterns so that you can adjust the placement of these churros, which move the perf board in the back, which can set your compression. I think right now we're at like 0.65 inches of compression on the fuel, and we found that that works great. Too little compression, and some shots would fly far, and some shots would be duds. We didn't try more compression than 0.65. It was kind of a case of it looked really good, so we just went with it. But to talk about the lower half of the shooter, everything from this bracket down is the Robotics 6 7/8 turret kit from AndyMark as well. And these two kits mesh together really well. Only a couple modifications had to be made between the spacing of how the two mechanisms meet. So apart from like mounting brackets and a few spacers, the entire turret assembly is commercial off the shelf from AndyMark, which we're really proud to have done and tried out. Unfortunately, we don't have control of the turret. It's not something that we got around to in our 72 hours. So we're running with a fixed angle, but we didn't find any issue with shooting fuel from 90 degrees or 45 degrees. There's no alignment inconsistencies as we're firing. Reese, do you have any other comments about the shooter?
Good.
If not, we can sort of run single ball tests and maybe try and drive our drivetrain. We're running the shooter at a fixed speed right now. Well, not even speed. It's really just a percent set point. So we're a little bit limited in our control, but we are powering it off of two Neo 1.1s, which are 1-to-1 with the 4-inch stealth wheels. And those are controlled by Thrifty Novas that you see on either side of the turret. But let's go ahead and turn it on. We're gonna have to drive the robot around a little bit to dial in our shot. But we found that this shooter setup is pretty consistent. We feel like a lot of the inconsistent shots that you're going to see are probably due to differences in fuel. It looks like we're in an okay spot right now. Looks like our shooter stopped for a second there, so we've got a fuel stuck in there. If you feed a second fuel through, can we just show that that unlodges the stuck fuel? So there's no real issue. There is a dead spot between the shooter wheels and the kicker where a fuel could get stuck, but since you're launching multiple game pieces, we found it to not really be an issue. The first one is just going to come out with a lower velocity because it's getting hit by the second one. Yeah, sure. Now we're going to test out a large number of fuel to see how multiple fuel back-to-back affects the range, or if it does at all. We didn't experiment with adding more moment of inertia to the shooter wheels, but that would potentially help in a test like this to become even more accurate. You can see some shots are long, some shots are short. With velocity control on the flywheels, I'll reiterate again, this is just percentage set point. With velocity control on the flywheels, you might be able to dial that in even more and get even more consistent results. But for right now, we're really happy with it. It's been performing really well.
One more cycle.
All right, we're gonna do one more cycle. One challenge with a turret type design is dealing with routing power and CAN and any other signals to the turret hood. Especially if you're going to try for 360 degrees of you can see some shots are short. That might just benefit from a little bit more velocity. But as I was saying, one of the challenges with a turret is always how do you get power and signals to the turret hood. And with our turret hood being limited to 180 degrees of travel, it becomes a little bit easier. We've just got an energy chain here sort of strapped to the hopper with enough slack that when it's rotated all the way to the left, the energy chain is taut, and then when we rotate all the way to the right, the energy chain kind of flexes the other way and bends out of the way. So with a 360 degree turret, this would take a little bit more consideration for us to figure out how. There are plenty of examples of previous robots that have 360 degree shooters without slip rings that are solving this issue with the energy chain, but in the 3 days we didn't really get around to experimenting and testing that.
Yeah, and I think like Corey mentioned, our current shooter is powered base %V. So as our battery power goes a little bit lower, we're going to be having a bit different shooting performance. So one really big key to unlocking the most performance and consistency out of this shooter is going to be more inertia and powering this off of speed control, and then a really good PID to basically maintain that speed. As you can see, when we were feeding one ball at a time, we were getting pretty consistent results. The goal is to be able to see those consistent results as we shoot a flurry of balls. But ultimately, we're really happy with the consistency. And what this has shown us is that we're basically in the corner of the alliance zone right now. You can see, if we're looking around us, we have basically the full alliance zone here. And this basically tells us that you can really shoot from anywhere in the alliance zone really effectively. And that comes really important into strategy and how it's going to play out. You can see as these balls are all around here, we basically are feeding all these balls around to us. Likely your partners can also be feeding you balls, and so being able to shoot from anywhere in the alliance zone is going to be really key. One really important factor to that is going to be also to have an adjustable hood. Right now our hood is fixed right now. We actually don't know what the angle is quite 100%. We were at 45 degrees, and then we drilled a new hole and adjusted a little bit lower. So we don't actually know what the new hole is, but we know it's a little bit lower than 45. So yeah. We can go ahead and do a couple of cycles right now. It's just showing the whole robot doing a bunch of intaking and then some shooting, and just kind of showing off the whole system working as a whole right now. Yeah, so you guys can see here, right now our shooter sticks out about an inch outside of our frame perimeter. And so this would actually make our robot illegal, as we are sticking outside our front end with our hopper. Packaging is a big challenge this year. So give yourself more room than you think you need, and just try and give space for everything that you're going to need. And don't design a turret that goes outside of your frame perimeter. And there's definitely a lot of things that we could do to solve this, like adding a 2x1 along the front rail of our chassis so that we can extend our frame perimeter by 1 inch, and that would help keep us inside the frame perimeter. But that's just one of our constraints of being 3 days, that hopefully this concept gets across, and then you can learn from what we've done here. So this is where having a faster intake would definitely be beneficial here. As we drive into the flurry of balls, we're getting some jams. And as you can see with the flexible hopper there, we're getting some bounce out. If we were able to make that more rigid there, we would be able to hold on to those balls a little bit longer. So as you can see with the %V, as we've gotten a little lower on battery, our shot performance has gone down pretty drastically. That's just where being speed control is going to be really, really important. So this hopper and intake system is designed around filling up the hopper fully. There's another viable strategy which you could do, which would basically shoot the balls directly into the back hopper and go for a smaller hopper and go for a more pass-through style. Very nice. We're going to do one more cycle. And we're also having a little bit of NavX issues right now with our gyro. So Corey's having a bit of difficulty driving the robot consistently. And we also have a bit of a lower speed on this, so you can imagine with a bit of a increased reliability, you'd have a bit better driving performance. So we had a really good flurry there at the end there. So that'll about do it for our cycles. So maybe this will be a good chance to go over some questions, or do you want to keep going?
Yeah, why don't we go over a few questions? I don't know if you guys want to do a battery swap too and stuff while we're going over some.
Let's do that.
So yeah, we'll take a quick break to do that. So a lot of questions on the hopper, so let's hop in. If you do have questions, Chad, if you're watching live, do put them in. We're going to get to as many as we can, but we also are going to try to cut off in about probably 15 minutes. Anyways, what is the max holding capacity of the hopper extended?
So it's a bit of a gray area on that, because in terms of the intake being able to bring those balls in, we actually can't do that right now because the balls continue to follow out of our hopper through the front. But if we were to ignore that issue, we are able to store 50 balls inside of this hopper.
And we did do a test earlier with that, so you can check out one of the many videos that have been posted on Fun in regards to that. A few other questions. One coming in from ER Munich asking, can the hopper handle a big hit while the intake is up because of the floppiness?
Yeah, so that's actually the goal of this. The floppiness is to actually be able to take a hit. I mean, this should be able to take a pretty good hit. You see from me kicking, it should be able to take a good hit from the front too. Everything is kind of designed around being really flexible. There's no metal being run besides these 1x1 angles here on the front side. So it's all designed around being super flexible. This polycarbonate roller has nothing on the inside, so that can flex a bunch. We knew that with our hopper being out the whole match, it was going to need to be flexible. It was going to need to take a hit. And so that was a really big design consideration for us. But it's a double-edged sword, right? Because now, because of that, we deal with this floppiness. And if we're going outside of our frame perimeter on the sides, that would make our robot, in another case, illegal. So that's where it was really important that we had these little arms right here, which help constrain. And so it's pretty close on if we're going outside of our frame perimeter, but I think with the arms, any movement outside of our frame perimeter on the sides would be pretty inconsequential.
What is the center, Benaya Hills asks, what is the center distance between the vectored wheels?
I would actually have to check the CAD on that one. Do you know that?
Yeah, I think if I remember off the top of my head, it's like 2.63 or something. It's whatever.
No, 2.63 from the
Oh.
two vectored center. No, it's probably like.
I got it.
Yeah.
Between the vectored rollers, I think we're sitting at like 3/8 or
They're saying from the
a
bottom one.
quarter inch of compression. So they're going to be like 5.75 or 5.625. We're going to have Reese measure right now. Let's see if I'm right.
7 3/8 minus 2 inches. It's 5 3/8.
All right, so we're running, 5/8 of compression.
And the goal with these is actually not to compress the ball a whole lot. You actually kind of just want to like kiss the fuel as you're kind of moving it through the system, and that's what works really well for the vectored intake wheels. It's also important to note that at the same time it's actually touching 3 faces at the same time. If we go ahead and remove some of these right here, I can illustrate that. Right now, when we're touching here, it touches the 2 intake wheels first. And there's about a 1/16 of an inch gap between the fuel and this back polycarbonate. And as we begin spinning, it touches on this back face and can then translate. And so there's really not a lot of force that's being put on between the ball and the vectored intake wheels, because this polycarbonate wall right here is limiting it from going back further.
Let's talk about the shooter a little bit. How are you adjusting range motor speed? And then another question that was asked by 300 Degree, what is the benefit of adding launcher hood control, and if so, how?
So we are controlling our distance right now via flywheel speed. You want it? Take it.
I can talk about this a little bit. So there's 2 different ways to really control how far and what kind of arc you're getting on the balls. As mentioned, one, there's the shooter speed itself, the flywheel speed, and then also kind of the hood exit angle. Right now, like we talked about before, we don't have an adjustment for the exit angle hood, so that's stationary. So we were just getting to, 3 days is kind of a lot of work. And we didn't quite get to it, but we were doing some linear interpolation. So basically what that is you go to a known location shooting on the field, we measure the distance between the center of our robot and the center of the hub, and then we just guess and check some fine-tuning values of the shooter speed. And you do that from a couple different spots on the field, key locations, things like that. And then with the code, you can basically say, these are our known shooting locations and motor powers. If you're halfway between those 2 values, use a motor speed that's halfway between those. So we've posted all of our code. I think that's not quite up on our GitHub, but it will be shortly after this.
Let's take one more question before we go and weigh the robot and do a few other things as well too. So in regards to your flywheel, there's a question that came in. Would you recommend a really heavy flywheel or the one that you guys went with? How did you go through the process of selecting this flywheel, and would you maybe select a different one?
Yeah, so as I mentioned previously, the process for selecting this flywheel was it's what came in the box, and it worked well enough for Ri3D purposes that we said, cool, it's good, let's go and run with it. It really depends on your feeder mechanism and how the fuel are entering your shooter. If your shooter is doing the bulk of the work to get the fuel up to speed, then you're going to need a huge flywheel. But since we have the hopper into the feeder into the shooter wheels, the fuel are moving by the time that they get there at a pretty consistent velocity, and it's on the flywheels on the shooter to do the last little bit of adjustment. So I think that this system could probably benefit from a little bit more flywheel and moment of inertia, but I don't think we would add much more.
All right, let's keep moving on. We'll grab some more questions in a little bit. We have some more demonstrations to do. We're going to weigh the robot, show some driving demos, talk a little bit more about code. What do you guys want to start with?
I think we should weigh the robot.
Yeah, take the battery out.
All right. Gonna turn it off. Maybe I'm not the person to be taking out the battery. I only have one hand. So right now the bumpers are mounted from the bottom of the robot, so we're not going to be able to take those off easily. But the max robot weight this year is 115, and your bumpers are allowed to be 15 pounds, if I remember correctly. It might be 20. These are definitely on the lighter side of bumpers. I'm going to guess these bumpers are 10 pounds. But all in, bumper plus robot were 108.6. So I'm going to guess the robot is like 98 pounds. This lines up with our first weigh of the robot. We were sitting at, 94, 95, and we've only added a little bit of weight since then, like the peanut bar and a few wheel changes. So I'd say we're sitting at 98 pounds pretty confidently. But let's go ahead and go back to the field. Do we want to talk a little bit about our strategy, or do we want to keep fielding questions?
You can talk about strategy and stuff always.
Yeah. So while we drive demo, do you want to talk about why we?
Yeah, so the archetype that this robot is really came down to flexibility. There's going to be a lot of ways that this game can play out. So there's two big considerations that we wanted to have with this robot. We wanted to have the ability to pass via from the neutral zone or the opponent alliance zone into our alliance zone, and we wanted to be able to shoot from wherever the robot is positioned. Excuse me. Secondly, we also know that winning auto is one of the biggest keys to winning matches in this game. If you can win auto, you immediately go into an inactive period, and that's actually a good thing because that allows you to collect balls, get more balls into your alliance zone for then scoring. And so after we've thought about it more, this robot could be maybe even more successful with actually a smaller hopper. Because if you utilize passing via your alliance partners passing to you, or you go in the inactive periods, you go to the alliance zone, throw tons of balls into your alliance zone, and then now, let's say you only have a capacity for 20 balls in your hopper. As soon as a ball goes into your hopper, it's immediately shot out via your turret and shooter and shot into the goal. And so now, instead of holding 50 balls and then going to go shoot 50 fuel, you're actually just constantly shooting fuel. So in this case, if we were to look over at this flurry of balls that are over here, the robot would basically just be able to drive through this, and all of these balls would go straight through the hopper and up and into the hub as we're moving along. So there's definitely a lot of really key ways to play this game. It's going to come down to just how well that you can package your robot and play the game. It's going to come down to your alliance partners, how well you play with them. But ultimately, we feel really confident right now that passing is going to be really, really big in this game. Considering, like, if for the same reason, if you're in the alliance zone constantly scoring, you can be in the neutral zone and you could choose a set point to be able to shoot to. Like, if I was in the neutral zone, I could say I want all the balls that I'm shooting to arrive right here. And so therefore, I can just be driving around and all the balls are aligning in the alliance zone. And then from there, I drive into my alliance zone and I have all these fuel here ready for me to start scoring with. And so ultimately, there's a lot of really good ways to play this game, but ultimately I think the passing is going to be a really big strategy to play this game effectively. And on top of this, our robot has no climber as of now, but we still believe this would be still really effective for us to have, and can only add to the effectiveness of the robot. So it's actually probably one of our best intakes.
Can you move that bar?
Yep.
We want to pass.
We're going to do a passing demonstration. This is new to me. So you can imagine if the robot's moving around a ton. It's important to turn on the shooter when passing. So you guys can see, you can basically, as long as you're not shooting across a net that's going to be here blocking, you can either choose a set point over to the left side of the alliance zone or right side of the alliance zone to be able to pass effectively. And then once you've passed, now you can then, during your inactive period, all these balls would be moving through the shooter at once while the turret is automatically tracking the goal. So let's just do a couple more cycles, just kind of showing off the robot and how it's performing. We're really happy with what we're seeing with the 3-day challenge. The name of this game is going to be testing and iterating and really squeezing out the most performance that you can with this robot, with your robot, to be able to do the things you want to do.
Hey, Reese, last night when we did the Monday recap, I think there was a little bit of not as much confidence in where you are now. What was the big change between then and where you guys are now?
Just sticking with the process. That's all it is. You know, we're not going to have all the answers, and you won't either. And you can see here our hopper is still dealing with some bugs right there. Our flanges that hold the hopper in place got a little messed up. Really, the process of this game is going to be testing and iterating and just dialing in your concept as much as you can. there's a lot of unknown variables to this game, so you just gotta try it, fail, and try again.
A really good question I want to ask that just came in. Did you find backspin on the ball consequential or beneficial? And any thoughts on additional wheels to minimize spin?
Yes, that's a great question that I've been thinking about a lot. So when shooting into the back of the hub, naturally, and then we saw this with 2022 also, you're going to be shooting into the rear side of the hub. And so having backspin is similar like in basketball. You hit the backboard, it shoots down into the basketball goal. So for that reason, we think it's very advantageous to have backspin. However, you know, you can also add, like for example, we're using a 4-inch wheel on as our main flywheel. You could add a 2-inch wheel on the top side where the perf board is right now to add compression. And that will reduce backspin, getting you more shot time. And I know a lot of teams did that in 2022 to increase a lot of shot consistency. So there's a lot of things you can play with. All right, so let's go ahead and fill up our intake one more time, and we'll go ahead and do some intake bump testing. Restart code. Okay. We are having some issues right now with our code where we do have to restart our reboot our restart our code every once in a while to re-zero our intake shooter. So you can see this Andy Mark stuff here is really, really good. That actually picks up a lot of carpet hairs and maybe other people's hair. This is really, really good stuff from Andy Mark. We've been nothing but pleased with this stuff. So highly recommend this to any teams. From what we've seen, it has some of the best material to material grip on the fuel. So overall, we're really happy with it. Okay, and that looks good. So we're gonna go ahead and fill up our hopper, and we're gonna do a bump test now. Yes, under the trench.
Yeah, let's do trench.
Let's go ahead and fill up our hopper, and let's drive under the trench. Like I mentioned before, we're having a little bit of gyro issues, which is affecting our ability to drive effectively. So it's important to note that when teams fill up their hopper, there's likely going to be some teams that have some overflow. All right, we're just going to go and drive through the trench now. And, we actually have to rip off our sponsor panel. It's bye sponsors. Yeah, so fuel tolerance is going to be a big thing. I don't know what the correct tolerance is going to be on the trench, but I know the tolerances normally are plus or minus ½ an inch. I imagine the trench will probably be a little bit tighter tolerance this year, but you can see we're going through it no problem. So our current height right now is at 21½ inches from the ground to the top. Our hopper is currently set at that, and also our shooter is set at that max height, and that basically defines kind of what our current overall height is going to be. So let's go ahead and overflow the hopper right now, and let's see what that kind of looks like. From our preliminary testing, we saw that, you know, if you have some fuel that's going over the hopper, you might end up decapitating a mechanism or causing a bind. In this case, likely what's going to happen, we're probably just going to lift the trench up and begin driving with it. So let's go and see that. So actually some fuel's just kind of getting decapitated from the system. If I go ahead and hold that steady, when you guys want to, thank you. Don't go too crazy. So there we got a bind, another bind, push through. So there the hopper being flexible kind of just moved out of the way there. All right, and so coming back to see if we can get another bind here. We're currently stuck on one. Yeah, so you're gonna have to be careful when you're doing a max fill hopper going through the trench. And for most cases, I think it might be best to actually put some sort of covering over your entire hopper and then take it over to the bump. So let's go ahead and see. This will be our first time driving over the bump with a full hopper, so we're all gonna see it together. We know we can't go at a slow speed or the chassis will bottom out, so I say let's just send it. Wait.
I can't. We lowered the speed.
Oh, we can't. We lowered the speed. So we may actually we're going to re-upload code to be able to drive a little bit faster right now. Going over sideways, we struggle, diagonally, we struggle a little bit with our slow speed. We're going to go ahead. Yes, so we're currently using the, we're running on our entire drivetrain, the Thrifty Bot inverted swerve drive with the TPU tread. And we'll go ahead and once we have a second, we'll show you what the underside of the robot looks like. We noticed this has amazing, amazing traction on the carpet, but not so great traction when it comes to the HDPE. A big benefit that you could get going to another wheel is potentially at Colson's, where they have really good grip on the plastic, or Black Nitrile would have really good grip. But it comes down to, are you willing to sacrifice some grip on the carpet to be able to get grip onto the bump? We're going to see if it really matters for us to have that grip here in a second. We'll drive backwards. Go ahead. Where our gyro's a little messed up, so he's doing his best. Looks like our drive speed is still a little slow. We're going to give it one more go. But definitely, all of these fuel added into the robot definitely increases the weight of the robot. So it'll be interesting to see what our traction kind of looks like going over it. We have any questions while we wait?
What's the bumper clearance?
Bumper clearance is 1 inch. So 1 inch from the ground. And that's basically, our chassis is higher than that. But the bumper is going to be the lowest point on the robot the whole way. And we tested this, and with just the chassis, it worked out well. There we go. So I think we're moving faster now. So we'll go and try backwards first. Whichever way. Oh, wow, we didn't drop a single one. All right, let's go forward. Nice, backwards. So this is, like I said, we're having some gyro issues, so we're having some trouble driving straight as of now. But as you can see, let's go and do a couple more tests and see how it does. We got some air on that one. There we go. So it's really important to note that if your hopper is full and you can't go under the trench, you have to be going over the bump. And so therefore, you got to make sure that your robot's going to be tough to be able to handle these bounces. I already foresee a lot of robots are going to be going over these, and maybe the first bump, the robot's dead. And we're going to try not to hit Tyler right now. Still driving? Awesome. Awesome. So that looks pretty good. Let's see if we can get fully stuck. No, we're able to get off. Try and get the robot stuck if you can. Yes. Oh. It's important to note that with the lighter drivetrain where we had less traction on the HDPE, we actually were able to get stuck, but it doesn't seem like with the fuel added in there, we're able to get stuck. Let's go and empty out the fuel and see if we can still get stuck. Colin, come over on this side. And let's go and empty out the fuel. Okay. My team just likes watching me throw balls out of the hopper. All right, let's go and see if we can get the robot stuck now. We're able to get off there. Awesome. So it looks like we're not able to get stuck, which is very nice. Awesome. Do you guys want to go ahead and wrap up, and we can go ahead and talk about code and talk about what's next for this robot, and everything that we want to improve and what our limiting factors is?
Yeah, so diving into the code, this year was a little bit new for us. We usually used a time-based robot, or the periodic one. This year we're using a lot of commands and command-based robot, and it's definitely a shift. We'd like to shout out the yet another software suite. Yeah, yet another software suite, and the yet another mechanism, yet another generic swerve library, yet another limelight. You might have heard those before, but they've been putting in some good work to help these, help make programming command-based robots a little bit easier. Jordan, do you want to talk a little bit more?
Sure, yeah. So we've programmed many swerve drives over the past, I don't know, what, 10 years. And like Corey mentioned, mostly in the iterative setup. So using kind of a framework library to do this, or a swerve drive generator, those kinds of things are kind of new to us. And so we had implemented some of the kind of like high level features that things like Yagzil and other libraries have, such as like cosine compensation, the skew, I forget what it's called, compensation. Yeah, so there's several different kind of high level features that a lot of these tools and libraries have that you might not have thought of before, and that might be, kind of harder to implement. So definitely, if you're new to swerve drives or mechanisms and things, we did a lot of the testing ahead of time in like simulation too. So it enables things like that as well. So yeah, definitely check them out.
And right into that, I'd like to start talking about improvements and things that we would like to change with this robot. One of the biggest ones, I think, would be more time with the robot for coding. We had a lot of ambition with the turret and swerve to be able to point towards the hub, adjust the turret, shoot on the fly, maybe even like pass to a fixed angle when you're in the center of the field. But we just didn't get around to getting those mechanisms to work and be under our control in the way we would need for that to happen. Reese, do you want to talk about some mechanical improvements?
Yeah, I think just to add a little bit more onto what Corey was saying about software, it's really going to be software that takes this robot from being an okay robot or a underperforming robot to be really a number 1 or number 2 seed at an event. Getting that automation going on this robot is really what's going to be able to take this robot to the next level. But in terms of mechanical fixes and improvements, I would love to make the robot legal in a lot of different ways. But this robot's meant to be a lesson to everyone watching and a lesson to us, and figuring out what works and what doesn't work. So as far as we see, there's a few improvements that we can make in terms of the hopper. Maybe the shooter we can leave extending out like that. But ultimately, we are pretty happy mechanically with what we're seeing. It would be amazing if we could eventually have an adjustable hood on this robot, and really be able to have really precise shooting and shoot from wherever we want with really good precision. And climber, we really haven't talked a lot about climber, but that was something we also missed the mark on this year with just getting caught up with the hopper and everything else. But there's a couple of different areas on the robot that are open for us to be able to mount a climber, but ultimately we just didn't have time to get it on. So we talked about this concept a lot, but never tested it. It was basically be angled telescoping tubes that would then extend up to the L1 rung and just climb like that. So there's definitely a lot of different ways that you can approach this game to get the L1 climb, but ultimately we didn't have the time to make this one fit for us. So that about does it. Do you want to have anything you want to add? Well, thank you to everyone so much for watching all of our videos and keeping up with us. It's certainly been a very fun Ri3D. Definitely been a lot of more unknowns this year than a lot of previous years, but we've been very happy with what we were able to produce and be able to provide the community with some insightful insight and showing a lot of the community what we did wrong, most of all, but also some of the things that we did get right. So we hope you guys all enjoyed watching us, and yeah.
Yeah, I'll just jump in real quick and say, for those who have had a chance to watch Cranberry Alarm, there are a lot of people that are kind of behind the scenes with this sometimes. You saw a few people on screen, but there are some awesome people that really make up this group, and all come in with that thought and process of, like, they're here to help benefit you teams and to go that route. I think Cranberry Alarm's done a fantastic job with that. We hope you all agree with that as well, too. So make sure you do check out all the videos that have come out, all the different explainers, the prototyping processes all the way through. It's not just about the finalized product. It's the journey that gets there as well, too. And hopefully you can translate that with your team as you tackle the rebuild system. So, guys, congratulations on a great build. We'll be filming more of a full reveal video, like a typical one, in just a little bit. But that is going to wrap it up for Cranberry Alarm here in the rebuild season. We can't wait to see teams how you do as well, too. And make sure you check out on Fun Robotics Network all the other great stuff we have coming, as well as there may be an appearance or two by the Cranberry Alarm robot here. Do we have a name picked out for this robot, or is that TBD still?
TBD.
All right. So keep an eye out for that, and we can't wait to see how this competes, and hopefully even more so what inspiration your teams are able to take out for it. By the way, if you are inspired by Cranberry Alarm, let them know. Many of them are at different competitions. They'd love to hear about that. And of course, on the Chief Delphi thread and other areas you may find content. So thank you everybody for tuning in. We wish you the best in the rebuilt season, and we can't wait to see how you do. Thanks, everybody. Thanks for watching. Don't forget to like, subscribe, and click the bell to stay up to date on future fun videos. AndyMark is your one-stop shop for all things in FRC Rebuilt. Be sure to stock up on your rebuilt game-specific elements right now at andymark.com. Plus, check out the newly released products to help your team, and don't forget to stock up on bumper materials and kits. Head on over to andymark.com to get the superior service and reliability that teams expect. Build your alliance with so many other FIRST alumni who go to Kettering University. Every student at Kettering experiences their cutting-edge co-op programs that seamlessly blend the professional and academic worlds. Kettering co-ops are a fully immersive working experience at the leading edge of industry. Head on over to kettering.edu/first to learn more about their incredible programs and to get more information.